Let's learn what is surface integral now. So surface integral, for that we will need a surface, and this vector is dotted with an area element, a surface element dA, and we integrate over it. And v, the vector, v must be a vector function. Integral over surface, the surface may sometimes include a volume. Then this symbol for surface integral comes into effect, v dot dA. With this symbol, it represents a closed surface integral that encloses a volume. Let's understand what surface integral is by working out an example. So we are given a vector function v equals 2x z x cap plus x plus 2 y cap plus y z cube minus 3 z cap, and there is a cubic box of arm length 2, and we are supposed to perform this surface integral over 5 sides of this box, excluding the bottom one. So let's draw the picture first. We have this type of a box. The bottom surface is excluded for performing this integral, and we will perform it over all the 5 surfaces. Let's name those surfaces. The front surface is 1, the backward surface is 2, right hand side is 3, left hand side is 4, the top one is 5. And let's perform this integral over different surfaces. For surface 1, the surface element dA, area element, is given as, here what are the, so this is x, this is y, and this is z. So what are the variable on the first surface? We can see that x is a constant, y and z they vary, and this surface points along the x direction. So this can be given as dy dz x cap. With this, v dot dA is given as 2xz dy dz, that is 4z dy dz, and if we perform the integral now, integration over v dot dA, that will be 4 times integration over 0 to 2 dy, because 2 is the arm's length, integration over 0 to 2 z dz. With this, so we have put the value of x equals 2 here to get this expression. Okay. Now, if we perform this integral, we will find that the value is 16. That's on the first surface. Similarly, we will perform integrals over all the other surfaces. For surface 2, we will have x equals 0 and dA would be in the first surface. We have forgot to mention that x equals 2. Okay, we mention it here. Here dA would be dy dz minus x cap. Because this surface is pointing in the negative x direction, the opposite direction, we consider the outside of the surface to be the direction of the surface. Okay. So v dot dA, this quantity becomes minus twice x y dy dz, and this is 0 because we have x equals 0. So, integration over v dot dA in the second segment also clearly goes to 0. Let's consider the third surface now. In the third surface, y equals 2 and dA is given as dx dy, sorry, y equals 2, so it's dx dz y cap. V dot dA can be obtained as x plus 2 dx dz. Therefore, the integral v dot dA on this surface is integration 0 to 2 x plus 2 dx multiplied by integration 0 to 2 dz. And if we work it out, integrate the x part and multiply that with the integrated value of the z part, we will get this quantity equals 12. Component 4, here we have y equals 0. With that, dA becomes minus dx dz y cap. So, v dot dA becomes minus x plus 2 dx dz. So, integration over v dot dA on this surface is minus integration over 0 to 2x plus 2 dx times integration over 0 to 2 dz, and this is minus 12. On surface 5, we will have z equals 2. So, dA becomes dx dy z cap, v dot dA equals y times z square minus 3 dx dy equals y dx dy, because z being 2, z square is 4 and z square minus 3 becomes 1, so it's y dx dy. Integration over v dot dA gives us integration from 0 to 2 dx, integration from 0 to 2 y dy, that is 4. Now, if we find the total flux, that is, we add contribution from 1, 2, 3, 4 and 5, we get that the total flux is 20.